For the ready portion of lesson 2.1, it's really dependent upon how comfortable you are with vocabulary. And what I mean by that is, do you know what the question is actually asking for you to do? I would encourage you to use vocabulary guide or a blue sheet if you have it, some sort of reference to be able to look things up. You have access to the internet. You should be able to identify a vertex, maximum, minimum, axis of symmetry. Like I said, there's a lot going on. So making a point on the vertex means that we are going to make a point when the function changes direction. So for number 1, I've made that point right down at the very bottom. So that would be the first one. And now I need to label the coordinates. So the coordinates of this would be 0, 0, as it is right at the origin. The next up, we're going to, I want to create an axis of symmetry. And so this is what this means. We need to try to figure out where, if I were to put a mirror, where would that mirror go so that the left side is a direct image of the right side, a complete reflection. So then, next up, we need to state whether this vertex is a maximum or a minimum. So if it's a maximum, then there are no outputs that can be greater than that 0. Well, if that's the case, this is a minimum because it will not go any lower than 0 for the output. The equation for the axis of symmetry would be x equals 0. Because all along that vertical line, x is equal to 0. Let's try a few more. I'm going to do a little bit more than I usually do for these ones. So for number 3, again, noticing and defining that axis of symmetry, and the vertex. So the vertex here would be -1, -2, because I go left 1 and then down 2 units to get to that point. So the vertex would be at -1, -1, -2. And again, because there are no outputs that are going lower than that, we know that this is a minimum. Next up, we're going to draw our axis of symmetry. There we go. And that axis of symmetry, or AOS, be x equals -1. Because this line right here is crossing -1 through an infinite number of outputs. Let's take a look at number 4. First up is identifying the vertex. So here's my vertex here at the very top. And that vertex will be at -1, 2, 3, 1, 2, 3, 4, 5. So that'll be the vertex, and because we know that that's the vertex, and if you notice here, it's going up and then down, so we know that it can't get any higher than that point. Therefore, this is called a maximum. Also, we need to include our axis of symmetry. And you'll be able to notice that the axis of symmetry is crossing, so AOS, crossing at x equals -3. Number 6. Number 6 is a tricky one because right about here is where that vertex is, where the parabola starts to change direction. And I'll be a little bit more specific or precise with that, and that's kind of why I want to do this one with you. So our vertex would be, we've got our 0, 0 here. It would be over 1 and then a half, and then down 1, 2, 3. So our vertex would be at 1.5, comma, -3. And again, because there are no numbers that are going any lower, any outputs that are going any lower, we know that this is a minimum. I'll clean that up a little bit. Finally, once again, we need to, create our axis of symmetry. And in this case, our axis of symmetry would be 1.5. So if you notice here, there is a correlation. There is a relationship between what you see in the vertex and our axis of symmetry. And it's no coincidence. Okay, the x value for the vertex is also our axis of symmetry. We're going to play around with that in a little while. For the next piece, we're talking about different representations. And I know that we haven't talked a whole lot about this, but some of these things we can do. We can actually take a look at, and we can see what we see, be able to represent that. So we're trying to match things up, A, B, C, and D to numbers 11, 12, 13, and 14. And what I'll do is I'll start with this, the top left. We can say that this can be valued as x squared, because we can say that this is x times x. Well, here's another one, x squared, and x squared. Therefore, if we add all of those together, we know that we should have 4x squared. That would be number 14. Okay. For letter B, we can set this up. This is our x squared. And if we were to set up the dimensions on the sides, these long rectangular pieces can be considered single units. And if you look at the top right, or the top and the side, you can also say that this is x plus 4, and this is x plus 4. So if I were to multiply those together, you would end up having x plus 4 squared, which would get you number 12. For letter C, when we have squares, we can set up their sides as x's. And then we can say, just like we did for letter B, what's happening along the sides. And what's happening along this side is that I've got 4 x's. This side here, I've got 4 x's. So together, to find the area, I'd be able to take 4x squared, which would give me number 13. For letter D, we know by default, process of elimination tells us x squared plus 4, but just to play around with this a little bit, we've got a regular size x, so we know that we have x squared, and then we can say that these are all single units because they're not the same size, so they would be x squared plus 4. For the go portion, things get a little bit more complex. We are supposed to plot each of these points and try to figure out what's happening here. So for number 16, we can go ahead and plot the points. I can't plot the 11 because it doesn't go up to 11, but I can plot the -2 at 6, the -1 at 3, the 0 at 2, the 1 at 3, and the 2 at 6. And I know that the 3 is going to go up even more. So I've got my graph created based on the table that I have, and I can say that in what way did the graph move? The graph moved up 2 units. What part of the equation indicates this move? So now I need to go back and I need to create this equation. So based on what I have here, I can see that my vertex, that vertex moved up 2 units from the original spot. What part of the equation indicates this move? We can say that the vertex moved up. For number 17, -4, 9. Would be up here. -3, 4 would be here. -2, 1. -1, 0. 0, 1. 1, 4. 2, 9. So now I notice that it's shifted, moved to the left 1 unit. So we know that, and this is something that we're going to continue working on, but if it's moving to the left, it will look like this. What part of the equation indicates this move? We can say that the vertex moved left. For number 18, same process. Plot those points. Zero, 9. 1, 4. 2, 1. 3, 0. 4, 1. 5, 4. And 6, 9. So taking a look here, we can say that our equation would be x minus 3 squared, because now it's moved to the right 3 units. And we can follow it up here, and we can talk about the vertex moved right and call it good. For the go portion, the first two should be very familiar. These are actually pulled straight, the blue sheet pulled them straight from the practice problems here. So I'm not going to do those two, but I will talk about number 21 and a couple others. So for number 21, when we're taking square roots, remember we're taking a square root of a thing and then another thing. So if we have, for example, the square root of 36, we know that we are taking 6 times 6 and pulling out one of those pairs. Well, for number 21, the pair that we have is actually x minus 16. So when we take a square root of that, we can pull one of those pairs, and it would give us x minus 16. For number 22, we have 36x plus 25 times 36x plus 25. Okay, that's what that 2 is saying. And we'll pull one of those pairs. And this is our solution. For number 24, a little bit more challenging. We're going to take what we've done and put it all together. So now 9 can be broken down into 3 times 3. M can be broken up into m times m. And 2p cubed minus q all squared can be broken down into 2p cubed minus q times 2p cubed minus q. And now we need to look for pairs. So we can take one of the 3's, one of the m's, and one of the 2p cubed minus q's, which would give me 3m times 2p cubed minus q. Hopefully this helps. I know this is a longer video, but there's a lot of stuff that goes on. Feel free to reach out with any questions you may have.